What if one of the first things you ever learned as a child is actually one of the most mysterious ideas in all of human knowledge? 2 plus 2 equals 4 seems so simple that nobody questions it. It feels like common sense, something obvious, something safe. But behind this simple equation lies a question that almost nobody stops to ask. Why does this rule work everywhere in the universe? Think about it carefully. When you say 2 plus 2 equals 4, you are not just counting objects on a table. You are not just talking about apples in your hands or stones on the ground. You are making a much stronger claim. You are saying this rule is always true. No matter where you go, no matter when you exist, no matter how far into the universe you look, on Earth, on the moon, inside a star, or in a galaxy so distant its light hasn't even reached us yet. So the real question is simple. How can something so basic be universal? And this is where things start to become strange. Because mathematics is not just something we discovered in nature. In many ways, we invented it. We observed patterns in the world, yes. We noticed that if you combine 2 groups of objects with another 2 groups, you get a larger group. But that is observation, not mathematics. Mathematics comes after that moment. It is the language we created to describe those patterns, a system of symbols, rules, and logic chains built on top of reality. So, we built a language, a human invention. And yet, somehow, the universe seems to obey it perfectly. And that is where the mystery begins to grow. Let's go back to the beginning, step by step, because the deeper you go, the stranger it becomes. Thousands of years ago in ancient Mesopotamia, someone needed to count their goats. The solution was simple. 1 mark on a clay tablet for each goat. 1 goat, 1 mark. 2 goats, 2 marks. This was not advanced mathematics. This was just accounting, pure record keeping. But then something changed. People started trading goats for wheat. Now you needed to calculate value. If 7 goats are worth a certain amount of grain, how do you measure it fairly? And from that need, multiplication was born. Not from philosophy, not from abstraction, but from survival and trade. Then came land division. If you want to split a piece of land between children, you need measurements, shapes, and areas. That is where geometry emerges. In fact, the word itself literally means measurement of the earth. At this stage, mathematics is still just a tool, a clever system humans created to manage practical problems, nothing more. If that had been the end of the story, nobody would find it mysterious at all. You would simply say, of course, math describes the world, we invented it to describe the world. End of discussion. But then something unexpected happened. Mathematics started doing things that had nothing to do with goats. Ancient Greek thinkers became obsessed with geometry. For them, it was almost sacred. They discovered something beautiful and strange. In a right-angled triangle, the square of the longest side is equal to the sum of the squares of the other 2 sides. The Pythagorean theorem. Simple, elegant, and provable. But then came a question that changed everything. What if both short sides are exactly 1 unit? What is the length of the hypotenuse? The answer is the square root of 2. And that number refused to behave. It cannot be written as a simple fraction. It never ends. It never repeats. It goes on forever in a patternless sequence. To the Greeks, this was disturbing. They believed the universe was built on whole numbers and clean ratios, order, harmony, structure. But here was a number that broke that belief completely. They called these numbers irrational, meaning literally without reason. And that was only the beginning. The discovery of irrational numbers didn't just create confusion, it shattered the belief system. The Pythagoreans had built their entire worldview on the idea that everything in the universe could be expressed through whole numbers and neat ratios. To them, numbers were supposed to represent harmony, order, and perfection. But the square root of 2 didn't cooperate. It couldn't be written as a fraction. It didn't end. It didn't repeat. It stretched on forever, refusing to settle into any predictable pattern. To the Greeks, this wasn't just unusual, it was deeply unsettling. If numbers were supposed to describe reality, then why did reality contain something so chaotic inside something as simple as a triangle? And the unsettling truth didn't stop there. Irrational numbers were not rare exceptions hiding in the corners of mathematics. They were everywhere. In fact, most numbers on the number line are irrational. The neat fractions humans love so much are actually the minority, like tiny islands in an enormous ocean of endless, patternless numbers. This changed everything about how mathematics was understood. What began as a system for counting goats and dividing land was slowly revealing something far larger, something that no one had planned for. Mathematics was no longer just a tool for organizing the world, it was exposing a hidden structure underneath it. Then came another shock, even more surprising than irrational numbers. Take something as simple and familiar as a circle. The ratio between its circumference and its diameter gives us a number we call pi. At first glance, it seems harmless, almost ordinary. But pi is not rational. It is not just irrational, it is transcendental. That means it cannot be expressed as the solution of any algebraic equation with rational coefficients. In other words, It doesn't fit into the simplest kinds of mathematical frameworks humans created. And yet, this strange number appears everywhere. It shows up in waves, oscillations, probability distributions, heat flow, and even quantum mechanics. A number born from a simple circle ends up controlling phenomena that have nothing to do with circles at all. At this point, mathematics is already starting to feel less like a human invention and more like something discovered, something that was always there, waiting to be uncovered. But the story becomes even more unexpected when we jump forward nearly 2,000 years. In Renaissance Italy, mathematics wasn't just an academic subject. It was a battlefield. Mathematicians challenged each other in public competitions. Their reputation, their jobs, even their survival depended on solving equations faster than their rivals. Knowledge was often kept secret, guarded like a weapon. One mathematician discovered how to solve certain cubic equations where the unknown is raised to the power of 3. Before he died, he passed this secret to his student. That student was later challenged by another mathematician, and the competition became legendary. In the middle of this mathematical rivalry, something completely unexpected appeared. While solving cubic equations, mathematicians encountered square roots of negative numbers, numbers that made no sense in the real world. What could it possibly mean to take the square root of -1? By definition, any number multiplied by itself becomes positive. So negative numbers had no square roots in the traditional sense. These values were dismissed as impossible, meaningless, even absurd. They were called imaginary. And for a long time, that word was meant as an insult. But mathematics doesn't care about intuition. It only cares about consistency. And slowly, something strange began to happen. A few mathematicians refused to abandon these so-called imaginary numbers. One of them, Raphael Bombelli, made a bold decision. Instead of rejecting them, he treated them like real numbers and followed the rules of algebra exactly as they were. He didn't try to interpret them physically. He simply asked, what happens if we allow this system to continue without breaking the rules? The result was shocking. The imaginary terms, instead of creating chaos, often canceled out perfectly. At the end of long calculations, the impossible parts disappeared, leaving behind clean, real answers. It was as if these strange numbers were secretly guiding the math through an invisible path. For example, certain cubic equations that had no obvious solution in the real number system suddenly became solvable. The final answers were completely real, yet the only way to reach them was through this impossible intermediate world. It was like walking through a tunnel that shouldn't exist, only to emerge on the other side in the real world. Still, most mathematicians were uncomfortable with this idea. René Descartes even gave them the name imaginary numbers, and he meant it dismissively. To him, they were just a trick, a temporary tool with no real existence, something to use and then discard. But mathematics had other plans. Over time, brilliant minds like Euler and Gauss developed these ideas further. They discovered that when you combine real numbers with imaginary numbers, you get a new system, complex numbers. These weren't just strange artifacts anymore, they formed a complete and consistent mathematical structure. Even more surprisingly, complex numbers could be visualized geometrically. They could be plotted on a plane, with one axis representing real values and the other representing imaginary ones. Suddenly, what once seemed impossible had structure, symmetry, and beauty. But still, no one believed they had anything to do with physical reality. They were useful, yes. Elegant, yes. But real? Absolutely not. That belief held for centuries. Then the 20th century arrived and everything changed. Quantum mechanics emerged, a theory designed to describe the behavior of atoms and subatomic particles. At its core was a mathematical object called the wave function. And this wave function wasn't made of real numbers. It lived in the world of complex numbers. That meant imaginary numbers were no longer just optional tools. They were embedded in the very foundation of physical reality at the atomic level. Even the equation developed by Erwin Schrödinger relied on this complex structure to describe how particles behave. At first, Schrödinger himself was uncomfortable with it. He tried to reformulate the equations using only real numbers. So did many other physicists. For decades, they attempted to remove imaginary numbers from quantum theory, but every attempt failed. Experiments eventually confirmed something unavoidable. Quantum mechanics cannot be expressed fully without complex numbers. They are not a convenience, they are not a trick, they are essential. And suddenly, the imaginary numbers invented in Renaissance Italy were no longer imaginary at all. They had become part of the structure of reality itself. At this point, the pattern becomes impossible to ignore. Numbers that were invented for abstract algebra ended up describing the behavior of atoms. Ideas that were once dismissed as meaningless turned out to be essential for modern physics. And this is not an isolated case, it keeps happening again and again. Take geometry, for example. For over 2,000 years, Euclidean geometry ruled mathematics. It described flat space like a sheet of paper or a tabletop. It was based on a set of logical assumptions called postulates that seemed completely obvious. But one of those assumptions, the parallel postulate, stood out. It was more complicated than the others, and mathematicians struggled for centuries trying to prove it from the rest. They failed. Eventually, in the 19th century, mathematicians asked a radical question. What if the parallel postulate is not true? What if there are multiple consistent geometries depending on how space behaves? This wasn't inspired by observation. It was pure logical exploration, an attempt to understand what mathematics allows, not what nature demands. Then Bernard Riemann entered the picture. In 1854, he presented a new vision of geometry that changed everything. Space, he suggested, does not have to be flat. It can curve, stretch, and vary from point to point. It can behave like a sphere in one region and like a saddle in another. To describe this, he developed powerful mathematical tools that allowed distances and angles to be measured in curved spaces. At the time, this was pure abstraction. No one knew what it was for. It seemed like beautiful mathematics with no connection to reality. Riemann himself could not have predicted what would come next. More than half a century later, Albert Einstein needed a new way to describe gravity. He realized that gravity is not a force in the traditional sense. Instead, it is the curvature of space-time itself. Objects move not because they are pulled, but because they follow the straightest possible paths in a curved geometry. But Einstein didn't have the mathematical tools to fully express this idea. Then he learned that Riemann's geometry already existed. The abstract mathematics created decades earlier fit perfectly into the structure of the physical universe. It became the language of general relativity, predicting black holes, gravitational waves, and the expansion of the universe long before they were observed. What began as pure mathematical imagination became the foundation of reality itself. And this raises the same question again and again. Why does this happen? Why do systems created in the human mind, often without any practical goal, end up describing the deepest layers of the physical world with such precision? The pattern keeps repeating, and with every repetition, the mystery only grows stronger. The story doesn't slow down here. If anything, it becomes even more surprising. After Riemann's geometry found its place in Einstein's theory of gravity, it became clear that abstract mathematics wasn't just useful for physics, it seemed to be waiting for it, as if the structure of mathematics was already prepared long before anyone discovered what it could describe. But another breakthrough was coming from a very different direction. In the early 20th century, physicists were struggling with a new problem: quantum mechanics. This theory described the strange behavior of particles at the smallest scales where classical intuition stops working. Particles don't behave like tiny billiard balls anymore. They behave like waves of probability, spreading out, interfering, and only becoming definite when measured. To describe this behavior, physicists introduced something called the wave function. This wasn't a physical object you could touch or observe directly. It was a mathematical description of probability itself. And here is where things take a turn that no one expected. The wave function is not built from ordinary real numbers. It is fundamentally complex. It depends on both real and imaginary components working together. At first, many physicists were uncomfortable with this. Even Erwin Schrödinger, who developed one of the central equations of quantum mechanics, was uneasy about it. He tried to reformulate the theory using only real numbers, hoping to remove what he considered a mathematical complication. Others tried the same thing. For years, there were serious efforts to eliminate imaginary numbers from quantum theory completely. But every attempt failed, not because of convenience, but because of necessity. When physicists tested the predictions, the full complex structure consistently matched reality. Any version of the theory stripped of imaginary numbers failed to reproduce the correct results. The conclusion became unavoidable. Quantum mechanics requires complex numbers at its core. This was a turning point. Numbers that were once called imaginary, invented in Renaissance Italy as a mathematical curiosity, were now embedded in the fundamental description of physical reality, not as shortcuts, not as approximations, but as essential components of how the universe behaves at its deepest level. What once seemed like mathematical fiction had become physical law. And yet, this is not an isolated case. It is part of a pattern that repeats across centuries. Time and again, mathematical ideas created for purely abstract reasons without any physical motivation end up describing real phenomena with astonishing accuracy. And the pattern continues to deepen. Because if imaginary numbers found their place in quantum mechanics and curved geometry found its place in gravity, then the question becomes even more pressing. How many more layers of mathematics are already waiting to be discovered in the structure of reality itself? By now, the pattern is impossible to ignore. We have seen numbers invented for abstract algebra become essential for quantum physics. We have seen purely theoretical geometry become the foundation of spacetime and gravity. We have seen mathematical structures developed without any physical intent later emerge as the language of the universe itself. And each time, the same question returns with more weight. Why does this happen? Take another example, electromagnetism. In the 19th century, James Clerk Maxwell brought together separate discoveries about electricity and magnetism into a single mathematical framework. Before Maxwell, these were considered unrelated phenomena studied in different branches of physics. Maxwell expressed them in a set of equations that describe how electric and magnetic fields interact. Changing electric fields create magnetic fields, and changing magnetic fields create electric fields. From these simple relationships, something extraordinary emerged. The equations predicted self-sustaining waves, oscillations of electric and magnetic fields that travel through space. When Maxwell calculated the speed of these waves using known physical constants, the result matched the measured speed of light almost exactly. This led to a shocking realization. Light is not separate from electricity and magnetism. It is an electromagnetic wave. Later, experiments confirmed the existence of other electromagnetic waves beyond visible light, radio waves, microwaves, and more. These discoveries eventually led to radio, television, radar, and wireless communication. All of it was already hidden inside the mathematics before any of it was observed. And again, the same pattern appears in a different form. Abstract equations predicting real phenomena long before experimental confirmation. Or consider group theory, a branch of mathematics developed in the 19th century to study abstract symmetries in algebraic systems. At the time, it had no known physical application. It was pure logic, built for its own sake. But in the 20th century, it became essential for understanding atomic structure and quantum mechanics. The behavior of electrons, energy levels in atoms, and even the classification of fundamental particles all rely on symmetry groups. In modern physics, the Standard Model, the most successful theory of fundamental particles, depends heavily on symmetry principles described by group theory. Again and again, mathematics developed without physical purpose becomes the exact language needed to describe physical reality. And this brings us back to the central mystery. Is mathematics something we invent, like a language or a tool, or is it something we discover, something already embedded in the structure of the universe, waiting for us to uncover it? Because if mathematics were only a human invention, we would expect it to be limited, approximate, or tied closely to human experience. Instead, it reaches far beyond us, predicting phenomena no one had ever imagined. This is what Eugene Wigner famously called the unreasonable effectiveness of mathematics in the natural sciences. Not just effectiveness, but unreasonable effectiveness. Because the more we explore reality, the more it seems that the universe is not just describable by mathematics. It seems to be written in it. And that leaves us with a question that still has no clear answer. Are we discovering the language of the universe, or did we invent it and somehow, against all expectation, the universe learned to speak it too?